So we want to consider the properties of roots and some of the etiquette of roots. So the first property that we want to look at is if I have the nth root of the product of two numbers a and b. This is relatively easy to figure out what it should be if we think about the exponents as fractional exponents. So from what we have just discussed, we could say that this is the product of a, b to the 1 over n power. Now, recall from before that when we had ab to the nth power, we said that that was a to the n times b to the n. In other words, we could apply the exponent to both of the factors in the product, because if we had the product n factors of ab, that means we have to have n factors of a and n factors of b being multiplied together. So now we'll just do the same thing with the fractional exponent. So if I have 1/n of a factor of the product AB, that means I must have 1/n of a factor of A times 1/n of a factor of B. Now, translating that back into the language of radicals, we could say that this is the nth root of A times the nth root of B. So in other words, if we're taking the root of a product, we can take the roots separately and then multiply them together. So let's look at a little example of this. Let's say that we had the cube root of 8x squared. So if we rewrite this as 8x squared to the 1/3 power, it becomes a little bit more obvious what we should do. We can say that we have 1/3 of a factor of 8 times 2/3 of a factor of x. So then what can we do with that? We can rewrite 1/3 of a factor of 8 as the cube root of 8 times, and then using our notation we can say this is the cube root of x squared. But we don't want to leave the cube root of 8 as the cube root of 8. We obviously want to simplify that to the number 2, because 2 cubed is 8, so the cube root of 8 must be 2. So this gives us 2 times the cube root of x squared. Now notice what we started with. This is a point of etiquette. 8 was underneath of the radical. In general, since 8 is 3 factors of 2, if we ever have a number of factors equaling the number of the root, mathematicians generally like to bring it outside. It's just considered a little bit more polite to do that. This could be, this is mainly for historical reasons, because figuring out, we didn't have calculators to figure out what the roots of various things were, like we do today, and it made life much simpler if we pulled things like 8 out of the cube root. So let's look at another rule here. Let's consider the rule, so let me change colors here. Our second rule is that the nth root of the rational number a over b is equal to the nth root of a over the nth root of b. Once again, this makes a lot of sense if we think about this in terms of fractional exponents. So ab to the nth root of a divided by b would be ab to the 1 over n power. And we should recall that we had a rule that said if I had a over b to the nth power, we could say that that must be a to the n over b to the n. And that makes sense if we have n factors of the ratio a to b. Then that means we would have to have n factors of a divided by n factors of b. So with that in mind, we can apply the same logic here. If I have 1/n of a factor of the ratio AB, I must have 1/n of a factor of A, and I must have 1/n of a factor of B. And translating it back up into radical notation, it makes sense that we could take the fraction underneath the radical and break it into two radicals. Now let's apply this to a situation. Let's look at the square root of 4/5. When we do that, it's often helpful to rewrite it, or at least think about it, as a half factor of 4/5. But this allows us to break it up into a half factor of 4 in the numerator and a half factor of 5 in the denominator, which we can rewrite in our more familiar radical notation as the square root of 4 over the square root of 5. We all know that the square root of 4 is 2, and the square root of 5 is irrational. Now, this brings up another point of etiquette. Mathematicians do not like to leave radicals in the denominator. So the best way to eliminate a radical in the denominator is to multiply your result by the radical over the radical, because the ratio of my multiplier is 1. So I'm allowed to do this, and you can see in the next step that would give me 2 times the radical 5 in the numerator. But when you take the square root of 5 times the square root of 5, it simplifies to 5. Now, why would we want to do this? Once again, this is historical. Now that we tend to just, if we want to know what the square root of 4/5 is, we probably would just put it right into our calculator as the square root of 4/5 and get something out to many decimal places. In the old days, we didn't have calculators, and you had to do all of this by long division. And if you've done much long division, you know that you want to have a very simple number as your divisor, and 5 is a simple thing to use as a divisor, whereas if you had an irrational divisor like the square root of 5, it would be extremely difficult to get what the result would be to many decimal places. Whereas dividing by 5 is quite simple, and so you could quickly get to the right answer if you had a value given to you of what the square root of 5 was to a lot of decimal places. The key is we would not want to be dividing by the square root of 5 if it were expressed to a lot of decimal places, because it would be a complicated divisor. So in modern times, I would just recommend, if you need to know what the square root of 4/5 is, just put it in your calculator. But historically, we would have tried to simplify this before evaluating it. The final rule that we'll look at in this video is the following. If we have the nth root of the nth root of a base A. Now, this is a big mess if you don't understand fractional exponents. But if you understand fractional exponents, this becomes quite simple. We can think of this in two sets of parentheses, I should say, as a to the 1 over nth power to the 1 over mth power. And when you write it this way, it becomes fairly obvious what you should do. Let's quickly recall that when we had a to the nth power to the mth power, we knew that the result should be a raised to the product of mn. This is because internally we had n factors of a, and then we have m groups of n factors of a, so we end up with m times n factors of a. We just do the same thing now with partial factors. So we would rewrite this as a, since we had 1/nth of a factor raised to 1/mth of a factor, we now have the product of those things, which would be a to the 1 over mnth power. Now, if we have a fractional power with a denominator, we know the denominator is the root we're looking for. So we could rewrite this as the mnth, the product of m times nth root of a. So I lose track of where we were going. If you saw an expression with a radical inside of a radical, you could quickly, by thinking about partial or fractional powers, figure out how to simplify that to a single radical. Let's take an example of this. Let's look at the square root. Notice there's no 2 written, of the cube root of 7. This could be intimidating at first, but if you rewrite it as 7 to the 1/3 power to the 1/2 power, in this case I didn't need the inner set of parentheses, you could realize that that would be 7 to the 1/6 power, which you could optionally write as the 6th power of 7. So those are equivalent expressions, and so they would have the same value. So depending on the problem, if you start it with the double radical, you should end probably using radical notation. Whereas if you start with exponents given, then you should end with an exponent notation.